Hello everybody, my name is Jimena Poco and I'm going to present Drift, a visual analytic tool for scientific literature exploration based on textual and image content. I'm going to start with the introduction, then the state of the art. I will present our proposal, which was evaluated with 2 case studies and 1 evaluation with users. I'm going to discuss the limitations and finally the conclusions. With the magnitude of publication, it is necessary to create information retrieval systems to facilitate the access to the scientific community. Systematic research, like the state of the art, is a time-consuming task. The user needs to analyze the content in depth to determine which articles are relevant or not. There are some search environments that provide visual tools, such as Visual Explorer from Microsoft Academic Research. Specifically, what is the problem? Exploring scientific literature can be a complex task using the traditional list-based paradigm, which does not allow to visualize relationships between the data and does not support an interactive analysis. It only allows text queries, leaving aside features such as images, charts, references, and metadata. These drawbacks hamper effective analysis, especially for users that do not know priori an exact set of terms for creating and require exploratory analysis to achieve their goals. State of the art on exploration of scientific article collection. We define a taxonomy with 4 method families. Citation-based method allow to find patterns through citations and analyze research collaboration. Textual content-based methods apply text processing strategies to establish similarities among articles. Image content-based methods involve images on the recovery information process. And finally, hybrid methods, devoted to combining 2 or more methods. Our proposal. We propose Drift, document retrieval based on image and textual feature. Our approach allows exploring volumes of scientific articles through multiple linked visual components that will reveal relations among documents by the analysis of images and text. It also allows you to interact with different stored states during exploration and finally obtain a set of filtered documents. We start with a collection of articles. We will extract and process textual and images information. This data will be the input for the second step, visual exploration. Visual exploration contains 2 main components, multi-CVIR. Each CVIR receives a query image and returns the most similar images in the entire dataset. We instantiate this CVIR up to 5 times, in our case, but it could be more. CVIRs are linked in a way that highlights images that share the same document. The second component is a multidimensional projection ordered by the text. Then, there is an interaction between these components, where we will easily be able to identify which documents are most interactive, are objective, and to know the images associated with them. To know the detail of the selection, we integrate visual components such as an author frequency, a word cloud that summarizes the topics, and a state machine that will store each selection and then allow us to combine or compare pairs of states. To implement this pipeline, we have built an interactive visual tool called Drift. Here we have an overview of Drift. On the left side, we can see 4 instantiations of CVIR with the most similar images. In the middle, a projection of the entire articles of the dataset are mapped. They are represented by circles. The blue circles represent the papers associated with the first CVIR, and so on. The green small circles represent the rest of papers. Users can make a selection, and the point selected will be painted in red. Below, we'll list the titles of such selection. To see more detail on the right side, we can see a frequency chart of authors. That's a word cloud with relevant topics, and a blue frequency bar chart with the years of the publications. Below, a string graph that stored selections. Each layer represents information such as a red one, the number of images, the yellow, the number of authors, and the green, the number of papers. I need at least 2 selections stored to compare both of them. Once selected, the states will be compared in this window. State Manager view. In the row A, articles shared by both states are listed. Next, their authors, a frequency of authors, and the images associated. In the row B, articles of the first selection that not belong to the second. And C, articles of the second selection that not belong to the first selection. Then, research can filter by checking the title of interest from each row. They will be displayed in the row D. Then he can create a new state. For text extraction, we use PDF to text from Popular Library. This tool converts PDF text to text files. Then we process the text by moving the stop words. We calculate a frequency vector, then we apply long cutoffs, and finally we obtain a TF-IDF vector representation. For image extraction, we use PDF to text tool. It converts each page of the article into 8-bit PNG. Later, using auto-linearization, a conditional determines if the components are images or not, if they are greater than 50 by 150 pixels. Finally, the images are processed by using AlexNet to extract feature vectors per image. We change the last layer from 1000 to 5 neurons to create 5 classes. Visual exploration. It is important to specify how we combine information of images and text. Our prototype starts with a multi-CVR that returns the most similar images. These images belong to documents. Well, let's remember that multidimensional projection takes textual features. These documents will serve as control points to conduct the projection. We use lamp projection technique because it's flexible for interaction. User can move the control points and then find new patterns. Case studies. Case study 1. The goal is to recover articles related to gravitational waves associated with supernova. We use the first data set. We start by entering 2 images associated with the objective. Next to it, we have the result of the respective CVR. At this point, we have important results. We can corroborate it by looking at the titles on the sites. These titles of papers are the control points mapped in the projection, and the rest of the papers, those in green, in order to them. If we select the blue control points, then we will see that they deal with gravitational issues. So we store it as a state right here. We make close selections and then move the control points close to find new documents. We see that they have varied topics, so it needs to be filtered. We filter and finally obtain 1 pair of states to analyze, 11 and 13. We will merge these states and filter them. We obtain this last state that we store our final result. On the right side, you can see the papers that include terms of gravitational waves, star, and supernova. Case study 2. The goal is to retrieve 3D modeling items. For this purpose, we use 4 queries associated with the objective and 1 non-associated to be used as a landmark, and thus conduct the projection by attracting articles not related to a region. We will use the dataset 2. We make selections around the control points and find interesting content in the word cloud, such as face, facial, skull, reconstruction. So we organize the control points as we observe. They attract instances and we make selections. In this case, we choose these 2 states with content that we care about, and we choose to filter them. We compare the states and create a cleaner one with only associated information. So far, in a few steps, we have already got articles for our results. In a new state. Once again, we reorganize the cover points, but in this case, we will reorganize the remaining ones and make a new selection. We make a small selection, and without having to compare it with another state, we can filter it by reviewing the titles or reviewing each paper by the bottom. If it does not correspond to the search, as in the second case, we eliminated it. And so we generate a new, more state already filtered. And filtering the first states, we obtain a total of 3 states with the following papers: texture in 3D, CPU, GPU, 3D, triangle, user evaluation. This evaluation contains 4 steps. First, introduction. The study is explained to the participants. 2, tool exposure. The functionalities and interaction of the components are shown. 3, user familiarization. Participants interact for 10 minutes with another dataset. 4, the evaluation. We invite the participants to carry out a specific search task. For this, we have got a team of six researchers, all of them with at least 1 postgrad degree in computer science and actively engaged in research. We define 2 questions focused on identify the particular group of documents. How many and which documents use human faces for rendering? And how many and which documents addresses volumetric representation of human body? Both groups perform the search activity, A1, using drift and list-based paradigm respectively. Later, they perform the second activity, A2, inversely. We compute precision and recall to evaluate the relevance of documents retrieved. Additionally, we store the elapsed times taken to accomplish the first activity and the second activity. In activity 1, by the list-based approach, researchers obtain a significant lower performance in terms of all measures. The difference between the best precision value for list-based and the worst for drift is close to 0.22. And even that, user 1 performs perfectly the test, obtaining a precision of 1. However, the elapsed time shown the user spent almost the same time close to the average value to perform this task. On the other hand, user 1 and user 2 of drift explained the lowest times for this experiment, except by user 3, that spends much more time. In activity 2, group 1 precision average was decreased, while group 2 was increased considerably. For instance, user 4, who obtained the poorest precision in A1, improved its performance, obtaining 0.75 of precision in A2. Limitations. Implementation into the web context aims to introduce a new paradigm into digital libraries exploration. The novel combination of multiple CVAR and multidimensional projection represents a flexible and powerful mechanisms to gather image and textual features into a methodology for document exploration. The feature extraction step impacts the whole process of analysis. It is crucial to have a valuable set of features describing images and text. Therefore, articles without images have a limitation with interaction with any CVAR component. Conclusion. We propose drift, a novel visual analytic approach for exploring scientific literature collections. Our approach combines textual and image features, improving the effectiveness and accuracy than traditional methods. Drift comprises multiple linked components such as CVAR, frequency histogram, word clouds, and SIBGRAPI. We demonstrate usefulness of our methodology in the 2 case studies and a user evaluation. Systematic research is a time-consuming task that can be reduced by including images and visual mechanisms. Thank you.